Unit 3 here. Unit 3 is going to take a little bit longer. It's going to take about 3 weeks for us here. This is a 12-week course, so that'll leave us with about a little over 4 weeks to do, closer to 5 weeks to do our 4th unit and 5th unit here yet. So anyway, today we're starting Unit 3. We're going to look at powers of 10. We know what it means to have something like that, 10 to the 3rd power. And it means we have 3 tens multiplied together. Now this exponent here that we called it has 2 parts to it. The 10 is referred to as the base. That's the number that's being acted upon. And in this case, the 3 is referred to as the power. That tells us how many times it's repeated. That 10 was repeated 3 times in that multiplication. Remember, an exponent is just repeated multiplication. What we're looking at today is we want to look at combining exponents with the same base. Call it with like bases. So that means it's going to be 10 to the power of, or x to the power of, for both numbers that we're trying to combine, both exponents we're trying to combine. I have 10 to the power of 3, and I'm going to multiply by 10 to the power of 5. 10 to the 3rd, of course, is 3 tens multiplied together. Fifth is 5 tens multiplied.
Okay.
And if we're multiplying those all together, we now have a total of 1, 2, 3, 4, 5, 6, 7, 8 tens being multiplied together. That's 10 to the 8th power. Now, many of you have probably seen before.
Yes.
Have probably seen before.
Works.
When we combine
Hi.
exponents with the same base, 10 to the 3rd, 10 to the 5th, both have a base of 10. When we're multiplying them, we add the powers. 3 plus 5 makes 8. So if I had 10 to the power of 13 times 10 to the power of 28, you don't have to write out all the 10s and count them up. We can go ahead and just add the powers. That's 10 to the power of 13 plus 28 makes 41. Got 10 to the power of 41. Now this can get a little trickier when we throw in the negative powers. 10 to the negative 8 times 10 to the 5th. Well, that is going to be 10 to the power of negative 8 plus 5. Negative 8 plus 5, we've got negative 8 and positive 5. That is 10 to the power of 3. Or if we have 10 to the power of 12.
Negative 3.
Negative 29. We have the same thing going on here. We have to add the powers. We're multiplying exponents with the same base. Again, these both have a base of 10. We've got a positive 12. A negative 29 is negative. It goes the opposite direction, and it's much longer. So we know we're on the negative side of 0 here. The difference between 12 and 29 is 17. So it's a negative 17. So 10 to the negative 17. Or we may have 10 to the negative 8th times 10 to the negative 15th. Once again, we have to add the powers. Base is going to see 10. We're multiplying those exponents with the same base. From 0, we've got negative 8 and negative 15. They go the same direction. So we can add their absolute values. Negative 8, or 8 and 15 add to make 23. So that's 10 to the negative 3rd. We might look at something like this. 10 to the 5th divided by 10 to the 3rd. Well, 10 to the 5th, of course, is 5 tens being multiplied together. And 10 to the third is 3 tens multiplied together. And if we use what we've learned about fractions, remember we can cancel out or divide out reducing by common factors. I can divide out a 10. I can divide both by another 10. I can divide by another 10. Well, on bottom, if I divide it by 10 3 times, I'm left with just 1. All the 10s have divided out. But it's not a 0. Remember, when we divide, we can only get ourselves down to 1. So that's a 1 on bottom. On top, we have 10 times 10, which is just 10 squared. So, of course, 10 squared over 1 is just 10 to the power of 2. Again, you've probably seen before that when we divide exponents with the same base, once again, these both have a base of 10, that we simply subtract the powers. 5 minus 3 gives us 2. So if I have 10 to the 29th divided by 10 to the 17th, again, I don't have to write out all the 10s and cancel them out. I can just subtract powers. They both have the same base of 10. So I keep a base of 10, and I'm going to have to subtract powers. 29 minus 17 gives us 12. So it's 10 to the 12th. So we might have 10 to the 51 divided by 10 to the 23. Again, those have the same base. They're both 10s. So when I'm dividing, I'm going to subtract the powers. 51 minus 23, 28. So that is 10 to the 28. Once again, these can be considerably more difficult when we throw in the negatives. I have 10 to the 14th divided by 10, negative 9th. We have to be very careful here. This is 10 to the power of 14 minus a negative 9. Well, minus a negative 9 14 minus a negative 9 is technically the same as 14 plus 9. That's just 10 to the power of 23. I have 10 to the negative 11th divided by 10 to the 14th. Well, again, I'm subtracting powers. I have the same base of 10. I have negative 11 minus 14. Well, negative 11 minus 14 can be negative 11 plus the opposite of 14, which is negative 11 and negative 14 both go the same direction. And negative 5. So we have to be extremely careful working with those negative powers again. Let's combine some division and multiplication together. Let's do 10 to the 18th divided by 10 31st times 10 to the negative 7th divided by 10 negative 19th, and see what we get. Order of operations here is a little fuzzy. Remember, we have to be careful that the fraction bar in each of these is an enclosing symbol. So what that means is we have to do everything on top of the fraction bar, then everything on bottom of the fraction bar before we divide. Well, here there's nothing to do on top or bottom of each fraction bar. Now, the other thing the fraction bar does is it tells us that division, this division, even though it's on the right side, has to come before that multiplication. Because of the enclosing symbol, it gives that division their preference because it's part of that fraction bar. So on the left side here, we have 10 to the 18th divided by 10 to the 31st. They both have the same base of 10. So we're dividing, so it's 18 minus 31, which gives us a negative 13. Still times. On the right side here, we have 10 to the negative 7th divided by 10 to the negative 19th. Both have a base of 10, so we're going to keep the base of 10. We have negative 7 minus a negative 19. Negative 7 minus a negative 19 is negative 7 plus the opposite of negative 19, which is positive 19. Negative 7 plus 19, like that, that comes out to be a positive 12. Now we have to multiply. We've taken care of the fraction bars. Now we have to multiply. We multiply, we still have the same base of 10. We have to add the powers. Negative 13 plus 12 is a negative 1. So that's just 10 to the negative 1. Negative powers. 10 to the negative 3. The negative power may not make much sense to us. How do we take something and multiply by itself negative 3 times? Well, just like we talked about with our multiplying negative numbers, we look for a pattern with our negative powers. If I had 10 to the positive 3, that's 1,000. 10 to the positive 2 is 100. 10 to the first power is 10. When I start with that base of 10, if I reduce the power by 1, my result over here ends up being divided by 10 at each step. So I keep going with that, and I reduce that power by 1 again. 10 to the 0, well, 10 divided by 10 is 1. Anything to the power of 0 is 1. Be careful with that. I have been known to be rather sadistic at times and do things like 10 to the 427th times 10 to the negative 811th, power of 42, 10 to the negative 193rd times 10, 8th, negative 17th power, power of 9, power of 0. What does this whole ugly mess equal? 1, because it's all to the power of 0. Anything to the power of 0 equals 1. I know, that's why I listen for revving engines in the parking lot before I walk out at night. So if we keep going with our pattern, reduce our power by 1, minus 1 is a negative 1. We divide by 10. 1 divided by 10 is 1/10. Going. 2, 1/10 divided by 10 is 1/100. Well, the same pattern when we were looking at our base value. 1,000. And we see a link here between 10 to the third and 10 to the negative third. They're just reciprocals. 10 to the power of negative 3 is simply 1 over 10 to the power of positive 3. 10 to the third is 1,000. 10 to the negative third is 1 over 1,000. That really is what reciprocals are. And that makes sense. If I multiply by something by 10 a negative 3 times, technically, I've divided by 10 3 times. So anyway, for right now, we're just looking at combining these powers some more. So let's look at something like 10 to the negative 14th times 10 to the divided by 10 to the 17th times 10 to the negative 29th. So here the fraction bar tells us we have to do what's on top first. So we'll combine those two. 10 to the negative 14th times 10 to the negative 8th. We're multiplying. They have the same base. Both are 10s. So that's 10 to the power of. We're going to add our powers. Negative 14 plus 8 is a negative 6. Now we have to do everything on bottom. 10 to the 17th times 10 to the negative 20. Again, they have the same base. They're both 10s. We're multiplying, so we're going to add the powers. 17 plus negative 29 is a negative 12. Now that we've done all that, we're left with just the fraction bar, so we have to do the division. 10 to the negative 6 divided by 10 to the negative 12. Well, again, we have the same base. Both have a base of 10. We're dividing, so we subtract the powers. Negative 6 minus a negative 12 becomes negative 6 plus a positive 12, which is just 6. That's 10 to the power of 6. Next, we might run into 10 to the third to the power of 4. Well, 10 to the third to a power of 4, an exponent to another power, well, that's just 4 10 to the thirds multiplied together. Well, 10 to the third is 3 tens multiplied together. So I have 3 tens there. Another 3 tens here. Another 3 tens. And then finally the last set of 3 tens. If those are all multiplied together, I have 1, 2, 3, 4, 6, 7, 9, 10, 11, 12 tens. That's 10 to the 12. Now again, most of you have probably been taught a shortcut for this. You have an exponent that is raised to another power. We multiply the powers. 3 times 4 is 12. If I have 10 to the 11th power of 14, I don't need to write out all those tens. That's a lot of them. I can just combine the powers. 11 times 14 is 154. That's 10 to the power of 154. Now you'll notice here I didn't say anything about having the same base because it doesn't matter. There's only one exponent here. There's only one base involved in this. So it's the powers that are being combined there because there isn't a second base to be considered. I might have 10 to the negative 5th power of 8. Well, again, I multiply the powers. Negative 5 times 8, it's going to be 10 to the power of negative 40. Or I might have 10 to the 7th to the power of negative 4. Well, again, it's 10 to the power of 7 times negative 4 is a negative 28. Or I might have 10 to the negative 6th to the power of 7. Again, 10 to the power of negative 6 times 7, oops, negative 6, 10 to the negative 6 to the power of negative 7. I have negative 6 times negative 7 is a positive 42. Now let's mix this all together a little bit. Say I've got 10 to the 9th times 10, negative 17th, over, let's do 10 to the negative 7th divided by 10 sixth, all to the power of negative 3. So here, we've got the parentheses, which means we have to start inside the parentheses. In there, there's another enclosing symbol. We have this fraction bar across here. The fraction bar says do everything on top first. Well, on top there, we have 10 to the 9th times 10 to the negative 17th. They both have the same base. They're both 10. Combine them. We're multiplying, so we add the powers. Positive 9 plus negative 17, 8. Now we also have to combine what's on the bottom of that fraction bar. It's another fraction, but it's just a simple fraction, just division. So it's 10 to the negative 7th divided by 10 to the 6th. Again, they have the same base, so I keep that base of 10. And we're dividing, so we subtract the powers. Negative 7 minus 6 to negative 13. Can't forget that power negative 3 outside there yet. So we got to put our parentheses back on and have that negative 3 out. Well, we still have stuff to do inside the parentheses here. We're going to do this division. 10 to the negative 8 divided by 10 to the negative 13. Again, both have a base of 10, so we can combine the powers. 10 to the negative 8 divided by 10 to the negative 13. Since we're dividing, we're going to subtract the powers. negative 8 minus a negative 13 becomes negative 8 plus a positive 13, which is 10 to the 5th power. First then to the power of negative 3 out there. Multiply the powers. 5 times negative 3 is a negative 15. 10 to the power of negative 15. We might have 10 to the 8th divided by 10 to the 12th times 10 to the negative 7th divided by 10 to the 5th over 10 to the 7th times 10 to the negative 11th divided by 10 to the negative 8th times 10 to the 15th, all to the power of 5. Once again, we have this parentheses, so we're starting inside there. Inside those parentheses, we have another enclosing symbol, this fraction bar. Let's do everything on top first. Now on top, we have two divisions to do. We have 10 to the 8th divided by 10 to the 12th. They have the same base, they're both 10, so we can subtract. 8 minus 12 is negative 4, times, we have 10 to the negative 7th divided by 10 to the 5th. Again, they're the same base, so we can subtract powers. Negative 7 minus a positive 5 is a negative 12. Now we still have to finish that off. That's still just working on the top of that fraction bar. 10 to the negative 4th times 10 to the negative 12th. They have the same base, so we're going to add powers. Negative 4 plus negative 12 is negative 16. That is the top of our fraction bar. Now let's do what's on the bottom of our fraction bar. Well, there's another fraction bar there. It is another enclosing symbol, so we have to do what's on top of that first. 10 to the 7th times 10 to the 11th. We're multiplying, we have the same base, both of a base of 10. So we add power. 7 plus negative 11 is negative 4. That's the top of that other fraction bar. Let's do the bottom. 10 to the negative 8th times 10 to the 19th. Again, they have the same base, so we can combine powers. We're multiplying, so we add. Negative 8 plus 19 is a positive 11. So that is 11. Now we still have to finish off that lower part of that original bigger fraction bar. We're going to divide those. 10 to the negative 4 divided by 10 to the 11th. Have the same base of 10, so we can subtract powers now. Remember, when we divide, we subtract the powers. Negative 4 minus 11 is the same as negative 4 plus a negative 11, to negative 15. Well, now, we have this to finish up here. We have to do the division inside. 10 to the negative 16 divided by 10 to the negative 15. They both have a base of 10 again, so we can subtract the powers. Negative 16 minus a negative 15. That is negative 16 plus a positive 15, or just a negative 1. So what we get there is simply 10 to the negative 1. Now that is still to the power of 5 out there. We don't have that done yet. 10 to the negative 1 to the power of 5. We multiply the powers. Negative 1 times 5 gives us negative 5. So that's 10 to the negative 5. Probably won't get quite that ugly with you on a test or quiz unless it's an extra credit question. There might be an extra credit question out there that's pretty miserable, pretty long, even worse than that. But again, that would be extra credit. For standard credit, I wouldn't expect you to do anything more difficult than maybe this one. Well, these powers of 10 are extremely important to us because we've talked about our place values. From our decimal point, going to the left, we have the ones place, the tens place, the hundreds place, the 1,000s, the 10,000s, And continuing on, 100,000s, whatever. Going to the right, we have the decimal places. But now that we've seen these powers of 10, you might recognize 10 to the 0 is just 1. 10 to the power of 1 is 10. 10 to the power of 2 is 100. 10 to the third is 1,000. 10 to the fourth is 10,000. 10 to the fifth is 100,000. 10 to the sixth is 1,000,000. 10 to the seventh is 10 million. And we keep going. Our number system is called a base 10 number system. Term decimal, deci stands for 10, based on 10. Base 10 literally means our place values, our exponents, base of 10. We keep going to the right of the decimal point, it's the same thing. Our 1/10, that's really 10 to the negative 1. Our 1/100th, that's 10 to the negative 2. 10 to the negative 3, 10 to the negative 4, continuing on. So, if we have some extremely large numbers like 4,700,000, one thing we do to shorten that up when we write, and maybe so we don't have to pronounce it all, is write it as like 4.7 million. Well, rather than writing 4.7 million, there's another way to abbreviate it. We just say 4.7, and instead of using the word million, we can just say it is the 10 to the sixth place. Many of you probably recognize this as our scientific notation. To do scientific notation, identify the first non-zero digit in the number. The 4 here. We move our decimal point to be after that first non-zero digit, so we move it there. And then we name the place value of that digit, which was 10 to the sixth. 4.7 times 10 to the sixth. Likewise, we might have 0.0003. Find our first non-zero digit, that would be the 3. So I'm going to move my decimal point to be after that, to be 3.2. Place value of that 3 is in the 10 to the fourth, or 10 to the negative fourth place. That's 3.2 times 10 to the negative fourth. That's how scientific notation works, is we are naming the place value of that lead digit, that first digit that's before our decimal point there. That's saying this 3, that is saying that this 3 is in the 10 to the negative fourth place value. We wrote that as a standard number. Now, we don't want to have to write out our place values every time we convert numbers from standard or decimal notation into scientific notation. So there's a shortcut. We notice here that in the 4,700,000, the decimal point started here at the end of the number. Ended up in here. It had to move 1, 2, 3, 6 places. Notice we have a power of 10 to the sixth. That was a large number. It was larger than 1. Our place values that are 1 or larger are positive powers of 10. That would be a 10 to the positive sixth. Over here, the decimal point started out right there. It moved to right there. It moved 1, 2, 3, 4 places. But now that number started out small. It was less than 1. Our place values that are smaller than 1 are negative powers of 10. So that is a negative 4, their power of 10. 0.2 times 10 to the negative 4. And that's the key. Numbers that are really small, in other words, smaller than 1, have place values that are negative powers of 10. Numbers that are larger than 1 has place values that are positive powers of 10. So if we go to convert, something like 710 million into scientific notation. First, we find that first non-zero digit, that's the 7, and we're going to put the decimal point right after. We list all the other non-zero digits, and if there's zeros with other digits after them, we list those too. 7.1 Everything that's left is a 0, so that's as far as we need to write. We don't write trailing zeros. We don't need those. Times 10 to the power of. To find our power of 10, we move the decimal point. The decimal point started out at the end of the number, moved it to here. It had to go 1, 2, 3, 4, 5, 6, 7, 8 places. Now, is that a positive 8 or a negative 8? Well, 710 million is a large number. It's larger than 1. So its place value is a positive power of 10. So this is 7.1 times 10 to the positive 8. So we have 0.000000029. Once again, we find the first non-zero digit. That's going to be the 2. So we're going to put the decimal point after that. 2.9. Now to figure out our power of 10, we have to figure out where the decimal moved. Now first, this is a small number. It's less than 1, so that means our power of 10 is going to be negative. Decimal point started here. It had to move 1, 4, 5, 6, 7, 8, 9 places to get there. That's 2.9 times 10 to the negative 9. 9. So we can convert from decimal or standard notation into scientific notation just that quick. Go the other direction. If I have 5.6 times 10 negative 7, and I need to convert that back into standard notation. Well, first I start out with my 5.6. Then I look at my power of 10. 10 to the negative 7. First of all, the negative tells me this was a small number. So to put it in standard notation, I'm going to make it smaller. 7 tells me I have to move 7 decimal places small. So I take my decimal place. To make it smaller, I move the decimal point to the left. So I move it over once. 1. Move it a second time, I add 0. So that's 2. Add another 0 for 3, 4, 5, 6, 7. So I have 0.12345 0.0000056 is that result. I might have 2.8 times 10 to the 5th. Again, I start out with the 2.8. 10 to the 5th, that's a positive power of 10, which tells me that this was a large number. Bigger than 1, so I have to make this larger. 5 tells me the decimal point has to move 5 spots. So from right here, to make it larger, I move the decimal point to the right. So I go 1. The second spot, I have to add a 0. So that's 2. Adding zeros, 3, 4, 5. So that's it. It's 280,000 as a standard number or decimal number. So for right now, we can convert between standard numbers and scientific notation fairly quickly just by moving the decimal point. But remember, it comes from place values being powers of 10. Now there's something out there called engineering notation. Our screen share just. Again. There we go. I don't know, for some reason my computer disconnected from the network for a second. Engineering notation is similar to scientific notation, only it's not limited to 1 digit in front of the decimal point. It's 1, 2, or 3 digits for the decimal. But however, it is limited to the powers of 10 are all multiples of 3. What do I mean by that? Well, let's take something like $42 million. I start out here at my decimal point, I move 1, 2, 3 spots. I have to move 3 spots at a time. I look to see if I can move 3 more, and I can. So I go 4, 5, 6 spots. I cannot move 3 more spots, so I'm done there. That's 42 times 10 to the 6th. So basically, I have to move my decimal point 3 spots at a time. Now, so when I'm going the other direction, that I have to be very careful. It can be a little bit confusing here. I have 0.00028. I start out moving my decimal point 3 spots, 1, 2, 3. And it looks like that's as far as I can go. However, I have to go 3 more, because right now, all that's in front of my decimal point is zeros. There are no non-zero digits in front of my decimal point. I need 1, 2, or 3 places that have to digits, and they have to be one of them has to be non-zero at least in front of my decimal point. So I have to go 3 more. So I go 4, 5, and then I go to the 6th one. I have to add a 0. 280 times 10 to the negative 6. Why would we deal with scientific notation? Well, because in electricity, we have volts, amps, ohms. If I think of that as being our main unit, I'll call it 10 to the 0, which is 1. We have milli. One of our prefix. Milli stands for 10 to the negative. We have micro. One of our prefixes. Micro is 10 to the negative 6. But we have nano. Nano is 10 to the negative 9. Go larger, we've got kilo. Kilo is 10 to the positive 3. Mega. Mega is 10 to the positive 6. If we kept going, we'd have giga, which is 10 to the positive 9. Tera is 10 to the positive 12. If we have something like 430, capital M is our abbreviation for mega, and that upside down horseshoe is ohms. We have 430 mega ohms. What that's really saying is 430 times mega is 10 to the 6th ohms. So when we do operations with those metric measurements, we can convert the metric prefixes, mega, kilo, milli, micro, nano, into their appropriate power of 10, and then we can work with them in engineering notation. Tomorrow we'll look at doing operations with numbers in scientific notation or engineering notation. Right now, I'll give you your homework. There are 3 pages. In your book, it is page 121, exercise 2.4. 45 the odds. That's just working with the powers of 10. Actually, that's just working with sign numbers, a review of negative numbers, so for the powers of 10. Page 125, exercise 2.5. 1 through 29, the odds, that is working with the powers of 10. And then our scientific notation is on page 130, exercise 2.6, 7 the odds. We have about 8 minutes left. If you'd like to get started on that, I'll be on the network here to answer any questions. Otherwise,